Hello, juniors. I hope you're doing fine. Today, we're gonna begin with a new topic for logic and statistics. This time, we're gonna be covering the logic part instead of statistics, and we're gonna be covering probabilities. This is a topic that you have seen already last year, and it starts kind of easy, but then as we go on with deeper probability definitions, you see that this gets a little bit more difficult, but always very interesting. Okay? So we're gonna start with a very basic class. It's about the basic definitions of probability. So the two objectives for today's class are first of all, understand the concept of trial outcome, equally likely outcomes, sample space U, and event, and number two, find the probability of an event A. Okay, so let's start by defining some basic things we need to consider whenever we talk about probabilities. It says an event is an outcome from an experiment. For example, if we talk about picking red color, the experiment is picking is from an option of colors. The event is actually picking color color red, for example, right? Then an experiment is a process by which we obtain an outcome. It's the process of obtaining the probability. Then a random experiment is one where there is uncertainty over which event may occur. We're always going to try to work with random experiments because that will ensure that we're gonna find the true probabilities of things, right? Whenever we work with a random experiment instead of a biased experiment, we could say. Okay, some examples of random experiments are rolling a dice 3 times, tossing a coin once, picking 2 cards from a pack of 52 playing cards, recording the number of cars that pass the school gate in a 5-minute period. Okay, so these are all random experiments in which we could determine the different probabilities about different events occurring in each of these examples. Okay? Then it says, we can express the chance of an event occurring using a number between 0 to 1. This is very important. A probability will always be between 0 and 1, okay? Where 0 represents 0% of occurrence and 1 represents 100% of occurrence, okay? That is, 0% means that the event will never occur, it's impossible, and 100% means that the event will always occur, right? It's a certain event. Okay, so on this scale, 0 represents an impossible event, and 1 represents an event that is certain to happen. This is called the probability that the event will happen, okay? So impossible, 0, even chance, for example, when we toss an unbiased coin, there's an even chance of getting heads and tails, and a certain event in which we're 100% sure that it will occur. And here's a TOK question for you to think about. Is there any 100% certain event that you could think about, like being 100% sure that it will occur that way? Try to think about some examples about that. Okay, then it says, we write probability of A to represent the probability of an event A occurring. Hence, the probability of A is always between 0 and 1. And you see that in both cases we have less or equal, right? Because an event could have 0% chance of occurring, or it could have 100% chance of occurring. Okay? Then it says a probability cannot be greater than 1. So when you work with examples, if you get an answer for a probability and you get, for example, 2.3, this is probably or most probably wrong, right? Because we can never have probabilities greater than 100%, which is 1, okay? Then it says, you can write probability as a decimal, fraction, or percentage, right? In this case, for example, the 1/2, we could also write it as 0.5, or we could also say this is 50%. Either way, as a fraction, as a decimal, or as a percentage, all of the results are correct, okay? We leave our answers in fractions because we're working with fractions, but it depends on you, basically. And it says, there are three ways of finding the value of the probability of an event. The first one is the theoretical probability. Then we have the experimental probability and the subjective probability. We're going to define each of these types of probabilities right now. Okay, so we're going to start with the theoretical, or also known as classical probability. And this is very simple. It says, a fair dice has 6 numbered sides, all of which are equally likely to occur. The list of equally likely possible outcomes is 1, 2, 3, 4, 5, and 6. Okay, just like a normal dice. We call a list of possible outcomes the sample space U. So here's another definition. Sample space are all the different possibilities I have in the universe. Okay, so we call this U, the universe. The notation NU equals 6 shows that there are 6 members of the sample space. Okay, there's 1, 2, 3, 4, 5, 6 different possibilities in my universe. So the number of alternatives is 6, right? Then it says, let event A be defined as the number 6. In this sample, there is 1, 6, right? So the number of possibilities for event A in this particular example is 1, right? It shows that there is 1 6 in the sample space. The probability of getting a 6 when you roll a dice is 1 out of 6, right? 1 out of 6. In probability notation, it is written this way. It's the number of alternatives for a particular event A divided by the number of alternatives I have in the universe, right? So this is basically the theoretical probability, right? The probability of getting a 6 is 1 out of 6 different possibilities when we roll a dice, okay? That's the concept of theoretical probability. So it says the theoretical probability of an event A is probability A equals number of event A over number of event of the universe, right? Where NA is the number of ways that event A can occur, and NU is the total number of possible outcomes in the universe, okay? Then it says, if the probability of an event is P, in N trials, you would expect the event to occur N times P times, okay? We're going to see this in an example just for you to understand what this is referring to, but it's actually very simple. I want to read this thing I found interesting. It says, probability theory was first studied to increase the chances of winning when gambling. Okay, so probability was invented, or the analysis of probabilities was invented because of this, right? Gambling. The earliest work on the subject was by Italian mathematician Girolamo Cardano in the 16th century. Okay, so that's just a little bit of history for you to know, cultural knowledge. Okay, so let's see this first example about theoretical probability. You see that this is very simple. It says, a fair 20-sided dice with faces numbered 1 to 20 is rolled. So it's a dice with 20 sides, okay? The event A is defined as the number obtained is a multiple of 4, okay? So part A says, determine probability of A. So probability of obtaining a multiple of 4, okay? So first of all, we need to define what is a multiple of 4. Multiple of 4. A multiple of 4 is any number that I can obtain by multiplying 4 times something by any other number, okay? So multiples of 4 would be 4 itself, because 4 times 1 is 4. Then we have 8, right? 4 times 2, 4 times 3 is 12, 4 times 4 is 16, and 4 times 5 is 20. And we will stop here because we have only 20 sides in this dice. So the relevant multiples of 4 would be these numbers over here, right? 4, 8, 12, 16, and 20. So we have 1, 2, 3, 4, 5 different alternatives, okay? So if we want to find the probability of A of obtaining a multiple of 4, it's, remember the formula. Actually, it's very logical, right? It's the number of event A divided by the alternatives I have in the universe, right? As we have seen here. So the number of event A would be 1, 2, 3, 4, 5. There are 5 different possibilities for event A. So 5 divided by, how many options do I have in the universe? 20 numbers, so divided by 20, okay? And we can simplify this 1/4, right? Yes, 1/4. So the probability of event A occurring is 1/4, which you could also write as 0.25, or you could also write this as 25%. Any of these answers would be correct. Okay, then we have part B. It says the dice is rolled 100 times. How many times would you expect a multiple of 4? Okay, so if I roll the dice 100 times and I know that the probability of obtaining a multiple of 4 is 1/4, then out of the 100 times that I throw the dice, how many would I expect to obtain a multiple of 4? It's the number of times I roll the dice times the probability, which is 1/4, right? So we're gonna write this as, we could write n to represent the number is I'm gonna write it like this: the probability, let me think about this. Probability, I'm gonna write it as probability of A times n, where n is the number of rolls, right? So we're gonna say this is n equals 1/4 times 100. We roll it because we roll it 100 times. If we roll it 200 times, it would be 200 and so on, okay? So 1/4 times 100, there's no need to use calculator for this. We can simplify the 4, this would be 1, and the 100 would be 25, right? So we would expect that the number of times we should get a multiple of 4 is 25 times. And pay attention to the word expect, okay? So if you do the experiment, you should expect to get a multiple of 4 25 times, but that doesn't mean that you are going to get for sure multiples of 4 25 times. We're always talking about probabilities, okay? The most probable thing to occur is that you would get 25 multiples of 4 when you throw the 20-sided dice 100 times, okay? That's the only thing we're finding here. So basically what we just did here is what is explained in this box over here. Let's read it again. It says if the probability of an event is P, in n trials you would expect the event to occur n times P times, okay? So I hope that is clear enough now. Okay, so that's it for theoretical or classical probability, right? Now let's go to the second type of probability, which is the experimental or empirical probability. This type of probability, well, actually both, the theoretical and this experimental, are widely used in the math projects that you're going to be doing next year, okay? So try to think about different examples or different types of projects that you can come up with where you use the concepts of probabilities. It's a very interesting topic to analyze for a math project. Okay, so experimental or empirical probability, it says, sometimes outcomes are not equally likely, but you can use an experiment to estimate probabilities. For example, to find the probability that a particular component that is being produced by a factory is faulty, we would test some components. If the first component we test is faulty, we could conclude that all of the components are faulty. However, this may not be the case. If the second component is not faulty, then we could conclude that the probability of a component being faulty is 1/2, right? Because 1 is not faulty out of the universe of 2 that we're analyzing currently, since half of the components so far are faulty. Okay, continuing this process a number of times and calculating the ratio, number of faulty components divided by number of components tested, gives the relative frequency of the component being faulty. Okay, so if we repeat this experiment probably like 1,000 or 10,000 times, we would get a more accurate probability of getting a faulty component, right? So that's what experimental probability is about, is trying or doing the experiment lots of times until you get a stable number for the probability, okay? We're going to be doing an experiment about this later on for you to finish understanding this concept, but it's very simple. Okay, so as the number of components of test increases, the relative frequency gets closer and closer to the probability that a component is faulty. So finally, it says you can use relative frequency as an estimate of probability. The larger the number of trials, the closer the relative frequency is to the probability. So that is what experimental probability is about. It's trying to replicate an experiment multiple times in order to get a more accurate value for the probability of something occurring, okay? So let's take this example. It says, the colors of cars passing the school gate one morning are given in the table. So we have different car colors and the respective frequency, which is something that was observed by this person, okay? So this person observed a total of 138 cars, and this person classified each of the cars by its color, okay? So it says for part A, I added this just to show you the concept of relative frequency. It says calculate the relative frequency of each color. Okay, so I'm gonna make a small column here for relative frequency. The relative frequency is basically the division between the frequency of a specific color and the total number of observations in this case, okay? So if I quickly do this, this is kind of messy, but it's okay. So the relative frequency is, in the first case, I'm going to do it small here. It's 45, this number divided by the total number, right? So 45 divided by 138. Let me write this properly to avoid confusion. So this is 45 divided by 138. Okay, and if you do this division, I'm going to use calculator for this to see if this simplifies. 45 divided by 138. This is actually 15 divided by 46. Okay, so this is the relative frequency for getting a red car. Okay, 15 divided by 46. And if we do the same thing for the rest of the colors, this would be 16 divided by the total, 138. This gives us 16 divided by 138, it's 8 over 69. And so on, okay? I'm gonna write the answer, 2 divided by 138. This is 1 over 69. Then 14 divided by 138, this gives us 7 over 69. 7 over 69. 17 divided by 138, that is 17 over 138. Then we have 23 divided by 138, this gives us 1 over 6. And finally 21 divided by 138 gives us 7 over 46. If you add up all of these relative frequencies, you should get as a result 1, okay, which is 100%. So you may try that. I'm going to do this. 15 over 46 plus 8 over 69 plus 1 over 69 plus 7 over 69. 7 over 69 plus 17 over 138 plus 1 over 6 plus 7 over 46, and this is 1. Okay, so this is correct. The relative frequency is 1, which is 100%, right? So this is correct. So this is what the relative frequency is about. It's basically the frequency of each number, of each color or variable, divided by the total amount we have in the universe. Okay, so that's the first part. So this is part A. Then we have part B, which says estimate the probability that the next car to pass the school gate will be red. Okay, if we have the relative frequency, the probability is directly that number over here. But if you want to think about the logical process, let me write this as probability of red. So I'm going to put an R. You could say that probability of obtaining red is the number of events for a red car in the universe, which is 45, right? Divided by the total amount of cars in the universe, which is 138. And you see that this is exactly what we wrote for the relative frequency, okay? So we can simplify this, and we would get as a result 15 over 46. And that is the probability of obtaining a red car, okay? You can write it as a decimal, as a percentage, however you want, but it's easier to work with fractions. Finally, for part C, it says, the next morning, 350 cars pass the school gates. So this is our N, right? Estimate the number of red cars that morning. So this is our N. We already have the probability of red cars. So the estimated number would be the probability of red cars multiplied by 350. So I'm going to write it as N. N equals 350 times the probability of red, which is 15 over 46, just as we did with the previous exercise. And if we multiply this, we can use calculator. 350 times 15 over 46, and this gives us it actually is a decimal number. It's 114.13. But since we're talking about number of cars, we can round this to the nearest integer, which is 114. So I'm going to write it as N equals 114 cars are expected to be red. Okay, so here you can see a real life application of probabilities, right? Probabilities is widely used to make predictions, okay? This is used a lot, for example, in forecasting when we want to know what the climate would be for the next days or the next weeks or the next month or whatever. We rely a lot on probabilities, okay? In order to determine what or the most probable scenario for a future event, right? That is the main application of probabilities. Okay, but as it is probabilities, it can always fail, right? You can always get an incorrect result later on, because we're always talking about probabilities, not about certain events, unless the probability is 100% or 0%, okay? Okay, so let's see the third type of probability, which is the subjective probability. And it says, you can't always repeat an experiment a large number of times. In these cases, you can estimate the probability of an event based on subjective judgment, experience, information, and belief. For example, Liverpool are due to play soccer against Arsenal in the English Premiership. Okay, so Liverpool and Arsenal are soccer teams, okay? What is the probability that Liverpool will win? You could look at past matches between the two teams as well as the last few games each team has played and how the teams have performed in the particular weather conditions the match will be played in. But eventually you will need to make a guess, right? So I think with this example, subjective probability is clear enough. It's when you just cannot make any or write any formula or a specific number that would tell you the exact probability of Liverpool winning Arsenal, right? Because we just cannot obtain information about that. We can just make a guess relying on past information that we have about matches between these two teams, right? But we know, and all of the soccer fans know this, that all matches are different, right? So we can never make an 100% accurate guess about who's going to win. We could kind of estimate or predict it by looking at on past information, but that's it, right? We cannot write a formula or do whatever calculation in order to see who has actual more chances of winning, right? And this is how the famous casa apuestas work, right? They rely on subjective probability in order to win money, right? Okay, so that's subjective probability. Finally, I wanna end this class by analyzing this TOK question for you, and I'm gonna leave this for you to think about. It says, when watching a crime series, reading a book, or listening to the news, the evidence of DNA often closes a case. If it was that simple, no further detection or investigation would be needed. Research the prosecutor's fallacy. You can investigate about what this is about, and you will see or understand this situation better. So the question is, how does reason contrast with emotion in making a decision based solely on DNA evidence? Or can we rely solely on DNA evidence in order to condemn someone? Do we need to analyze other things, other situations, other actions, other evidences, whatever? Okay, so try to think about this question. You can investigate about the prosecutor's fallacy and read about it. Very interesting math projects could also be done using this fallacy. I strongly recommend you to read this, and you'll see that it's interesting. Okay, so that's it for today's class, juniors. I hope this was clear enough. And if not, please let me know. We're going to cover the doubts during the following live sessions. Okay, see you.